I want to encourage you to go to Files, Unit 1, and look at worksheets. And I provided you with many more worksheets than the dry lab. The dry lab is doesn't have any line drawings. All my worksheets, other than the dry lab, have line drawings in it, including the answers. Now, if you're doing some of these, and we haven't got to the alcohols part like today, just skip that problem and come back to it. Okay. All right. So that's where they're located. Files, Canvas files, worksheets, Unit 1 worksheets. Okay. So let's jump into alcohols now. Now, the thing about alcohols, they're very, very different than alkanes and alkenes in terms of their polarity. They have very high intermolecular forces, and they're going to remain the most polar molecule so far up until we get to organic acids, and they're even more polar. But up until we get to organic acids, they're the most polar, the highest intermolecular forces. Hence the highest boiling point, highest melting point, highest surface tension. Now, there's 3 functional groups we're going to talk about in this unit. Alcohols, ethers, and aromatic alcohols, which include phenol and some others. Now, the big thing is that ethers are very different than alcohols. The major difference is the OH group as opposed to a COC group. So we've got all right, anytime now. I'm going to restart this application here. Now, why isn't this working? Oh, I know why. Power just went off. Oh. Okay. All right. Now, with alcohols, the main functional group is an OH called a hydroxyl group. Now, the big deal on a hydroxyl group is something called hydrogen bonding. Now, if we look at a chart of electronegativity values for all the elements of the periodic table, this is what it's going to look like. The most electronegative is fluorine up there, and it's got a value of 4.0. The least electronegative is cesium or francium down here. So bottom left, top right. So the closer you are to fluorine, the more electronegative. Now, what does electronegativity mean? Theoretically, you cover that in 305, but just in case, electronegativity, it is the tendency for an atom to attract okay, the tendency for an atom to attract a neighboring atom's electrons. Higher electronegativity, the more it wants those electrons. And it has to do with the stability of a full shell. You remember doing the 1s2, 2s2, and all that stuff in 305. It has to do with that. But don't have to worry about why it exists. That's what it is, okay? So the fluorine will gain the most stability by gaining an electron, either by sharing or transfer. Cesium, on the other hand, on the bottom left, or francium, gains the least amount by attracting electrons. Hence, its electronegativity value is the lowest. Now, where these values come in, this will determine whether the bond is polar or not. So if we look at the difference in electronegativity between the two atoms of the bond, if it's greater than 0.5, it's considered polar. So if we look at OH, okay, the oxygen value up here is 3.5. Hydrogen is 2.1. So if you look at the difference between the hydroxyl group here now, it's 1.4, a lot higher than 0.5. Hence, the intermolecular forces are very strong with that. In fact, whenever we have a hydrogen bonding to oxygen or nitrogen, it's considered hydrogen bonding because that electronegativity difference is the greatest. Think about water. Water's got two OH groups in it. So that's why it's particularly polar. Water is like almost like an acid. It's so polar. If we look at just an O oxygen bonded to a carbon, the difference there is 1. So it is also polar. So the bottom line is, I want you to think in this class, whenever you see oxygen in a molecule, it's usually polar because its electronegativity is so high. So if you think about things like that's glucose. So based on what I just said, do you think glucose is very soluble in water? What do you think? Yes, that's right. Why do you think it's soluble in water? Because of the what? Yes. So if water's polar, what must glucose be? Polar. And why do you think it's polar? Looking at its structure. Exactly. OHs, all that oxygen in there, all that party with the oxygen, that molecule very polar. Hence, that's why when you put sugar in your coffee, it dissolves right away. Like dissolves like. Now, this is not sucrose. Our unit 2, we're going to delve deeply into carbohydrates. And you're going to learn the difference between sucrose, glucose, fructose, mannose, a whole bunch of stuff. All right. And then if we have a carbon-hydrogen bond, the delta electronegativity there is 0.4, so it's considered non-polar. Now, if we look at the electronegativity scale as a continuum, it goes from 0 up to about 2 something. And it's all gray. There's no spots. It's just a continuum. We look at a carbon, okay, carbon's going to be 2.5. That means a carbon-carbon bond would have 0 polarity or 0 delta En. Hence, when we have carbon-carbon bonds, that's a very non-polar. Okay, that's why alkanes, based on this analysis, are so non-polar, because all they got is CC bonds and CH bonds. CH bonds are 0.4, CC bonds are 0. When you add all those bonds up, basically none of them are 0.5. And 0.5 is just the demarcation point for where we get to polarity. So in other words, a 0.5 is not a super polar molecule, but it starts to enter polar enough. 0.45 is considered non-polar, but it's starting to get pretty polar because it's getting close to that 0.5. All right. Now, alcohols play a predominant role biologically. They are OH groups all over the place on biological molecules. Now, the thing about biological molecules, they tend to be kind of big and complex. So if we look at cholesterol, it's a big molecule and has an OH group on it. So is this considered a polar molecule? Okay, right off the bat, you say Ferguson says OHs are really polar. That's right. That part of the cholesterol is polar. However, it's got all this other stuff that's very non-polar. So there's always a balance in biological molecules. How much is non-polar versus how much is polar? Cholesterol is considered non-polar. That's one of the reasons it builds up as plaque in your arteries and veins, because it precipitates out of blood, which is mostly water. But it's definitely an alcohol. And it's, you know, it's an alcohol by its OL ending. Menthol. Now, menthol is more polar than cholesterol because the amount of non-polar stuff isn't as much as cholesterol. because cholesterol has a whole bunch of stuff beyond the OH. And menthol, now this is what gives that minty taste to a lot of things like menthol cigarettes. This is what they add to cigarettes to make them have a minty fragrance. And then if you look at plain old ethanol drinking alcohol, it's got the big OH there and hardly any non-polar parts. Hence, the OH now dominates the ethanol in terms of polarity. That's why when you mix ethanol and water together, they mix quite readily. Another name for that is called vodka. When you look at a bottle of vodka, you don't see, oh, that's ethanol and that's water layers. It's totally homogeneous. So, albeit the OH is very polar, but you have to consider the whole molecule. Is the whole molecule dominated by nonpolar, or is the whole molecule dominated by polar functional groups? Okay, naming. Okay, naming alcohols, the functional group is an OH. So we have 3 parts. And let's stick a menthol group here, or methyl group here. Okay, so let's name that. First thing is always backbone. Okay, so it's 6 carbons long. It's a alcohol, so it's an OL. And we have a branch at carbon number 2. So it's going to be 2-methyl hexanol. Now you're going to see a pattern on naming. 3 parts, always 3 parts. First part is branching, which can be optional. Middle part is backbone length, number of carbons. And the last part is the functional group name. We can have multiple OH groups in a molecule, like ethylene glycol. It's called antifreeze. It's got two OH groups on it, 2 carbons, 2 OH groups. You'll find a lot of biological molecules have multiple OH groups. Biological molecules usually don't go by IUPAC naming because it's too complicated. Usually they go by common names that are accepted internationally. So if we were to name this guy here, let's make that a diol. Okay, first thing, 6 carbon backbone. Two functional groups. So it's going to be a diol. And those are positions 3 and 5. And we have a branch at 2 and 4. So it's 2,4-dimethyl 3,5-hexadiol. As far as the aromatic compounds go, remember aromatic has to have benzene in it to be called aromatic, or a benzene derivative. So phenol looks like this. Now, phenol is special with alcohol. When we get into acid, organic acids, we're going to talk about what is an acid, what's not an acid, what's a base, what's not a base. Now, the thing about acids is they disassociate a hydrogen ion. And the only alcohol that disassociates a hydrogen atom is a either a phenol or a phenol analog. So basically what we're saying then is phenol is a weak organic acid. So in water, water will pull that hydrogen off the OH group. It's the only one that'll come off. This is real important. The only one that'll come off is off the OH group. Now, benzene's got other hydrogens. There's a hydrogen here, 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 and here. Those stay on. Only the one on the OH group comes off. So if you have a benzene with an OH group, then the base molecule is considered phenol. And then everything is based on numbering for the phenol. The OH group on phenol is considered carbon number 1, always. Now, something that's important about alcohols is there are classes of alcohols. And it has to do with how many hydrogens are attached to the carbon that the OH group is attached to. It's either 2, 1, or none. Okay, if it's a primary alcohol, that means the OH group is on the end. Okay, so this is terminal. Only. So primary alcohols, for example, ethanol is a primary alcohol because it's on the end. Secondary are in the middle. And they have 1 hydrogen. Okay, so terminal hydroxyl carbons have 2 hydrogens. Now, this is important because when we start oxidizing alcohols, a hydrogen has to come off. So that means primary alcohols have 2 hydrogens. It can be double oxidized. Secondary ones in the middle only have 1 hydrogen. Hence, they can be oxidized once. Tertiary alcohols have no hydrogens. So they can't be oxidized, which is a wet test for testing whether you got a primary, secondary, or tertiary alcohol, is to see how oxidizable it is. If it's easily oxidized, or is it not oxidized at all? If it's not oxidized at all, it's definitely tertiary. If it's easily oxidized, it's primary. If it takes a while to oxidize, it's secondary. We have a wet lab on that. Okay, so this is real important. Because when we get to reactions, if we want to make something, we got to start with the right alcohol. And that'll come up in a little while here. We get into more detail on reactions. Okay, physical properties of alcohols. It's dominated by hydrogen bonding. That's what dictates the intermolecular force behavior of alcohols. That very strong hydrogen bonding. Hence, alcohols have very high boiling points and very high melting points and have very strong surface tension. Okay, like I was talking to you about cholesterol being a nonpolar molecule, even though it's an alcohol, we've got non-polar parts and polar parts. So it depends on the molecule. The key number is 7 carbons. So if we look at a graph, where we have butanol, 4 carbons long, it's dominated by the OH group. Pentanol, hexanol. When we get to heptanol, heptanol now has non-polar groups, even though they're weak, but there's enough of them to dominate polar OH. So heptanol is a non-polar alcohol. Hence, it won't dissolve in water. Hexanol dissolves fine. Isopropanol, rubbing alcohol. You see that all the time mixed with water. It's never 100% isopropanol. It's always some percentage, usually 50 or 95%. Okay, so 7 carbons. If we have a pure small alcohol like ethanol, 100% ethanol, you'll get hydrogen bonding. We have a dilute ethanol solution like vodka, 50% water, 50%, you'll also get hydrogen bonding. It's those OH groups, super, super strong, and they attract one another. Now, you're going to see a whole series throughout the semester on these graphs. And these graphs talk about classes of molecules. On the very bottom are alkanes and ethers and alkenes. They have the lowest boiling points based on their mass. The alcohols up at the top have the highest based on their mass. So if you consider a molar mass of, say, 40 grams per mole of an alcohol and 40 grams per mole of an alkene, the alcohol will have a much, much higher boiling point, melting point, and surface tension. And we're going to find ethers are in the middle. So we're going to, each time we have a new functional group, like after alcohols comes aldehydes and ketones. So we're going to fit them in as well in this graph. This graph's going to keep building bigger and bigger and bigger. When we get to organic acids, they're going to be even higher than alcohols. All right. So that's physical properties, intermolecular forces, and naming for alcohols. We haven't talked about ethers yet. Okay. Are there any questions about that? Now we're going to jump into reactions. Okay. Now, if you have an alcohol, and we want to, now remember, alkanes are very stable, alkenes or not, relative to one another. This first reaction, we're creating an alkene. That means we're going from a stable molecule to an unstable molecule. Whenever we do that, we have harsh conditions. In this case, the harsh conditions are sulfuric acid, 180 degrees Celsius. Those are harsh conditions. Hence, we've got to put a lot of energy into this molecule here to convert it to something that's less stable. Okay, so what's going to happen is we're going to take off a water. So basically, we've got to find two things to pull off a water. We have to find a hydroxyl group and an adjacent hydrogen on the next carbon over on either side. If that's the case, under the conditions of 180 degrees C, sulfuric acid, we can make an alkene. So it's called a dehydration or an elimination reaction. We're eliminating water. Let's do some simple examples here. Let's take okay, so we're going to take ethanol. What is that noise? Is that outside or sounds like a jet coming? Okay, so let's take ethanol, 180 degrees in an acidic environment. You could write H2SO4, or you could just write H plus. Either one's fine. Normally in organic chemistry, we use sulfuric acid a lot. So frequently, instead of H plus, they'll put H2SO4. And it depends. It could be concentrated, because we're going to be using concentrated acids sometimes in this class. And you've never done that before in 305. Use very, very mild, weak acids there. Never concentrated. 306, we're going to use concentrated acids. Very, very risky. Okay, so we got ethanol, hot temperature, acidic environment. What's going to happen? So can we find water on that molecule? Okay, first thing is to find the OH group. Okay. Number two, we have to go to an adjacent carbon and find an H. So are there any H's over here? There are three of them. So now we have what? Okay, so the big deal here is to find water. So if we know we have water, OH and an H, in those harsh conditions, we can pull that water out and create an alkene. Now, with this simple reaction, we don't end up with a mix. The problem is frequently we have a mix. So in your flow diagram, I have a little nomenclature that says expect mix. So let's look at it. Are there any questions about how we got this reaction? So it's ethanol, ethene, and then of course, you don't have to label water, but so we have reactants, products named, conditions. Always 3 parts to every reaction. Okay, so let's do a little more complicated one. Are any questions about this so far? Okay, so let's go ahead and do a little more complicated one. So we've got, what is this guy here? 1, 2, 3, 4. So that's a butanol, and it's on carbon number 2. So that's 2-butanol. 2-butanol under 180 degrees in an acidic environment. Will anything happen? Yes, because I can find water on that molecule. Okay. The problem is I can find it in 2 places. On either side of the hydroxyl group. So we have it here, and we have it here. So we're going to end up creating a mix. We're going to create 2 alkenes because we have 2 sources of water. Okay, the first one's going to look like this. I immediately draw the backbone. Backbone's not going to change. Okay, and this will be the blue one. Okay, so on either side of the OH group, we can find water. So either side of the OH group, we're going to end up forming a double bond and a mixture. In good old mixtures, we have to figure out which is more stable. Okay, so we do use the old Markovnikov and symmetry. Okay, so top one, symmetry, yes. Markovnikov, we have 3 and 3. So that would be yes. Okay. On the bottom one, Markovnikov, we have 3 hydrogens, 2 hydrogens. So that's 5 hydrogens. So compared to the 6, that would be a no. And it's unbalanced, so it's not symmetrical. So that one wins out. Everyone see why it wins out? It's got 2 things going for it. It's very symmetrical because the double bond is in the middle. And we have 3 hydrogens terminally, 3 hydrogens terminally. That's 6 altogether. The bottom one's got 3 and 2, 5. So Markovnikov rule says more hydrogens, more stable. Now we have to name them. Okay, let's just name them with a color. Okay, so the top one up here, we have 1, 2, 3, 4. So again, it's going to be a butene. And it's at position 2. So that's 2-butene. And this is a butene on the bottom as well. And is a position 1, so it's 1-butene. So we have reactants named, conditions, products named, mixture, more stable ones circled. All right. How do you guys feel about that? We're getting more and more complex reactions. Now, your book goes into something called mechanisms. Our class, that is out of the scope of our class. We're not going to talk about mechanisms. If you take OChem, the whole year's class, the 420, 421 series, you focus on mechanisms. Like every day you'll talk about mechanism. Okay, but that's one less thing in your life to have to worry about. So don't worry about when they start moving these electrons around and all this stuff. You are going to skip that. Okay. There's another reaction involving less harsh conditions than 180 in acidic. It's 140 in acidic. Things happen differently at that lower temperature. We do not create an alkene. We create an ether. So again, an ether is a COC set of bonds. It's got oxygen in it, so it's going to be a polar molecule, not as polar as an alcohol because it doesn't have hydrogen bonding. Because here we have a carbon bonding to an oxygen, not a hydrogen. So it's not hydrogen bonding. Okay. So what happens is the OHs stick together. So if you've got two ethanols in an acidic, hot environment. Now 140 is still hot. It's way above boiling. Pretty hot still. What's going to happen then? You're going to form an ether. What happens is the OHs stick together. So that carbon and that carbon are going to be stuck together with an O. I'm going to kick off water as well. All right, so at 140, we're going to stick the two alcohols together at their OH groups. So those two, the carbons attached to each OH group will be stuck together via an ether bond. So this would be ethanol, ethanol. Now, we can name ethers two different ways. The easiest way we're going to use is through something called an ethoxy bond. So ethoxy. Eth, because it's two carbons long, could be methoxy, one carbon long. So this is an ethoxy functional group off of ethane. Okay, and it's off of carbon number 2. So it's 2-ethoxy ethane. That's IUPAC. Okay, the common name would be diethyl ether. Common name is much easier to understand. So we're going to use the common name more so than the IUPAC name for ethers. We don't run across ethers very often. See you later. Okay, so that's all there is to ethers. Take the two alcohols, stick them together, and those carbons attached to the hydroxyl groups form a COC bond. All right, we okay with that? Now, I normally say that when you're synthesizing something, the backbone remains the same. So if you're synthesizing something with a 5-carbon backbone, you need to start with something with a 5-carbon backbone, except ethers. Because ethers, you're adding molecules together. So there, you have to look at each side of the ether backbone-wise, and that's what you start with. All right. And just did that one. All right. Back in 305, I'm sure you talked about oxidation and reduction. And you probably learned that oxidation is the loss of electrons. Reduction is the gaining of electrons. Same thing happens in OChem, except we don't talk about electrons, we talk about hydrogens. So oxidation in OChem is the loss of hydrogens. Reduction is the gaining of hydrogens. It's the same thing electronically. It's just they like to look at hydrogens rather than electrons in OChem. So are alcohols susceptible to oxidation? Yes, but it depends on what kind of alcohol. Not alcohols are created equal, like we talked about, primary, secondary, tertiary. So it depends on the alcohol, the classification of the alcohol. So now when we talk about oxidation, we're going to use this here. We're not going to specify it's potassium dichromate, potassium manganate. We're just going to say O in parentheses. Reduction is an R. So we don't have to worry about these oxidizing agents here. Now, primary alcohols are on the terminal end, and they have 2 hydrogens attached. That means they can be oxidized twice because they can lose 2 hydrogens. Secondary alcohols in the middle have 1 hydrogen attached, hence it can be oxidized once. Tertiary alcohols have no hydrogens, so they can't be oxidized at all. In primary alcohols, the first oxidation is an aldehyde. And I'll show you what that looks like. The second oxidation that takes the aldehyde to the carboxylic acid or the organic acid. So primary alcohols, boom, go to acids. Secondary alcohols go to ketones. Tertiary alcohols do nothing. Now, a couple things about that. This is how breathalyzers work. At a traffic stop, if a officer suspects that you've been drinking, they may ask you to, would you be willing to take a breathalyzer? And this is what happens inside the breathalyzer. It takes your breath And if there's any primary alcohol in there, like ethanol, drinking alcohol, it will attempt to oxidize it. And there's a color code in there as to the degree of color as to how much alcohol is present, but it's an oxidation reaction. I've been on jury duty a number of times. It's always for DUI. And the defense attorneys always ask me as they're going through the jury selection process, what's your career? What's your profession? Oh, I'm a chemistry professor. And they go, do you know how a breathalyzer works? I go, yeah. I said, do you want me to tell you how it works? Or they said, no, we believe you. And then the judge asks, do you know of a way to beat the breathalyzer? I go, yeah, it's really easy to beat it. The old Listerine was like 20% alcohol. So as you're stopped, you take the Listerine out of your glove box, gargle with Listerine, and you're going to get a really high test on the breathalyzer. But it's from the Listerine, and they don't know if it's from the alcohol or from the Listerine. So you've totally debunked the breathalyzer. Then the defense lawyers will usually dismiss me right away. Every single time. Happened like 15 times over my life. Additionally, in your liver, you have an enzyme called alcohol dehydrogenase. Alcohol dehydrogenase, guess what it does? It converts ethanol into an aldehyde. And then there's another enzyme called aldehyde dehydrogenase, which converts the aldehyde into acetic acid. And then your kidneys, you pee out the acetic acid. That's how your body eliminates alcohol in your liver. Now, there's a problem with that. Is you have two enzymes, and you have to have enough of those enzymes in your body to clear your liver of alcohol. And for whatever reason, genetically or whatever, you don't have enough of those enzymes, or you drank a whole bunch of alcohol, it may linger in your system. And the bad part is aldehydes are very, very bad for you because they're not particularly stable, and they'll tend to mess things up. That's what causes cirrhosis of the liver, are the aldehydes there. The converted alcohol over to aldehydes, which creates the damage to your liver. So if you don't have enough aldehyde dehydrogenase to oxidize that aldehyde to an acid, you're going to suffer damage. So our bodies have a nice way of getting rid of it. It's just that we can't overdo it. That's why they say, so many drinks an hour or whatever. And if you go over that, then your liver has a problem trying to get rid of all the alcohol. Okay, so primary alcohols, aldehyde, the acids. Secondary goes to a ketone, and tertiary, there's no reaction. So let's look at some examples here now. Okay, so we've got is that a primary, secondary, tertiary alcohol? Is it on the end? Yes or no? Yes, so it's primary. Is it in the middle? No. So primary alcohols have two hydrogens on the end. That means it can be oxidized twice. First oxidation turns that OH into an aldehyde. An aldehyde is a double bonded O. But it doesn't stop there. Second oxidation goes to the acid. Okay, so aldehydes and ketones are in unit 2. So you don't have to name an aldehyde until we get to unit 2. So you just put aldehyde there. And of course, we have to name the reactant, which in this case is a 3-carbon primary alcohol. So that's going to be 1-propanol. Okay, so on the end now, again, there are 2 hydrogens there. Each one of those can be oxidized independently. On the aldehyde, there's 1 hydrogen left, so it can be oxidized. Okay, so first test is primary, secondary, tertiary. That'll tell you how many times it can be oxidized. Second thing is we're going to duplicate the carbon backbone. 3 carbons, 3 carbons, 3 carbons. And we're going to be putting that O there, and that is an oxidizing environment, which could be permanganate, dichrome, a whole bunch of oxidizing agents. Okay, we okay with this? So it's backbone, 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 OH to aldehyde to acid. Now, if it's a secondary, so by the way, an aldehyde has got a it's got a carbonyl group on the end. The acid has got carbonyl group plus an OH for the organic acid. Now that's unit 3. We do a lot of stuff with acids, and we get into lipids. Okay, so let's look at a secondary alcohol. Two propanol in oxidizing conditions. Okay, so it's a secondary alcohol. That means it has 1 hydrogen here. Means it can be oxidized once. So the OH is converted to a carbonyl group. And that's called a ketone. So if the carbonyl group is in the middle, it's a ketone. If it's on the end, it's an aldehyde. And this is the chemistry of carbohydrates, by the way, aldehydes and ketones. Okay, so we have reactants, products named, and conditions. And then if we have a tertiary alcohol, which has no hydrogens, it can't be oxidized. It's just then no reaction. So again, no hydrogens by the hydroxyl group, no oxidation possible. Okay, so if we have a test, and we're going to do these tests when we do the wet lab on alcohols. If you have an oxidizing agent, and it undergoes reduction because that's what oxidizing agents do. They oxidize things. They have to be reduced themselves. Something's going to happen to it, so you know the reaction occurred. Color change, bubbles, heat, or cold, all those are indicators that a reaction happened. Usually with oxidizing agents, there's a color change. So okay, so we're going to take that oxidizing agent and dump it into our container that contains a alcohol. Now, in this case, it says it's an ethanol, so it's a primary alcohol. Primary alcohols can be oxidized. If they can be oxidized, that means the oxidizing agent has to change in some way. In this case, it's a change in color. So it goes from that orange over to this, I don't know, blue-gray or whatever. So the oxidizing agent did have a reaction. So that means it was a positive test for either a primary or secondary alcohol. And you don't know which, you just do know that it's been oxidized. Okay. If we look at our flow chart now, let's clean this up here. So alcohols can undergo dehydration to form alkenes or ethers. They can be oxidized to form aldehydes, ketones, and acids. Okay, so and remember, all these arrows also have the opposite reaction. So really, if we're trying to figure out how to make something, we want to use the opposite arrows. Okay, so if we're trying to synthesize something, you have to flip the arrows around. So if we have, let's okay, how would you make that acid? Well, let's see here. How long is the backbone? Well, we have 1, 2, 3. 3 carbons long. We want a 3-carbon acid. How do we make that? Well, because I gave you the product and how to make it, we have to use the opposite arrows. So here's an acid down here. And how do we make that? Well, we have to back up. Looks like we're going to start with an alcohol based on the reverse arrows. Okay, so we're going to have a 3-carbon alcohol to make a 3-carbon acid. Now the question is, which 3-carbon alcohol? Primary, secondary, or tertiary? Which do you think it'll be? Follow the reverse arrows. on carboxylic acid at the bottom, go backwards. What's required? Primary or secondary or tertiary alcohol? Primary, right, exactly. So that 3-carbon starting alcohol has to be a primary alcohol. If it's secondary, we won't make an aldehyde or an acid. It'll only make a ketone. And what kind of environment are we talking about? It's an oxidative environment. So this is a primary alcohol. So this would be 1 propanol. And we're just going this is propionic acid, but it's an acid. The main thing, it's three carbons. You're ending with 3 carbons, you want to start with 3 carbons, except for ethers. Okay, so we have reactants, 1 propanol, conditions, oxidizing conditions, product. So that's why this flow chart comes in so handy when you're trying to make stuff or you're trying to backtrack. Use forward and reverse arrows. Let's try how do we make that? First of all, what is that? Remember when the carbonyl, the CO, the carbonyl is in the middle, it's called a ketone. So find ketone on the chart. I'm going to back up. Okay, 1, it's going to be oxidative conditions, and it's going to be a secondary alcohol. All right, so let's look at backbone. Okay, we have a 4-carbon backbone. And a secondary alcohol. That means the OH group is in the middle. So we have secondary alcohol oxidizes to a ketone. Now, this has no hydrogens here. That means it cannot be oxidized further. The aldehyde has an H there, so it can be oxidized again. Okay, so that's why this flow chart is really important. And again, you can use it on your tests. And I have a unit 1 flow chart, I have a unit 2 flow chart, unit 3, etc. This keeps building. And this is why every test in here, except for test 1, is cumulative. Because you got to build upon past stuff. Which is why try not to get behind. It's really hard to catch up in here. Okay, so let's do some more examples. This example here is a multi-step one, and I want to hold off on that. Okay, so let's say let me see here. What we have. I'm looking for the flow sheet. Um, um, okay, I guess I can't find it. Oh well. Okay, so let's practice this some more. Um, Now this would be a typical test question, for example. I would say, um, you know, how do you make that? And you use your flow chart. And reaction problems are worth more points than naming and intermolecular force. And remember, every test is going to have three parts: intermolecular forces, naming, reactions, every test. And remember to maximize your easy points, labs, to go against your test points. So a point in lab is a point on a test. They're equivalent points. So you want to maximize those easy points, go against your test points. Okay, so let's make some more stuff here. What happens if we have so if we take propanol and subject it to 180 degrees acidic conditions, does anything happen? Okay, and whip over to your flow chart. Here we have an alcohol, 180-degree temperature, so we make an alkene. Same backbone. Three-carbon backbone. Now, an alcohol, 180 degrees, we need to find water. So we have OH, find that first, then go to an adjacent carbon, which is the only one that's here, and that has two hydrogens on it. So now we have water. So we can pull it off. We end up creating a double bond where the water molecule was. Okay, so we have reactants, product name, so that's propene. And conditions are 180 degrees acidic conditions. Now, if you get into your worksheets, you'll have lots of these examples. Also, your textbook has got lots of examples. Remember your textbook, skip the mechanisms when they're moving little electrons around. And get yourself some highlighters. He's got a nice set of highlighters. Yeah, identify the backbone. Different color for the functional group. Okay. All right. So that's what I wanted to cover today. Alcohols and ethers. 99% is alcohols, a little bit on ethers. Okay. All right. And start time for lab is not 3, it's 2:30. I've got to update the syllabus to reflect that. Last semester it started at 3. I just assume it's going to start at 3 again. the department chairman comes up and he says, "Oh, Tom, can you teach 306 in the fall?" I go, "Sure." He said, "It's identical to fall." Okay. It was online. Lecture was online last fall, in person here. It was Tuesday, Thursday. Monday, Wednesday last semester. Tuesday, Thursday. Different start time. Nothing's the same except for 306. Any questions about anything? Okay. I'll be posting this video today.